Alright, so in this video for chapter 17, we're going to talk about the effects that arise when you add some acid to a buffer and how that affects pH. We're also going to talk about buffer capacity and buffer ranges. Okay, so in this first topic, we're going to take a look at what happens to the pH when we add 1 milliliter of 0.1 molar hydrochloric acid to either 10 milliliters of pure water or 10 milliliters of buffer. And we're going to use the same buffer from the previous example, that nitrous acid sodium nitrite buffer. Okay, so let's look at what happens to the pH when we add acid to pure water first. Okay, so HCl is a strong acid, right? HCl is strong. So only comes apart. Right, the only thing that it comes apart, and it's got a Ka of 10 to the 7, which is a pretty substantial Ka, right? Remember evaluating the magnitude of the K constant. If K is really large, pretty much only the forward reaction happens. If K is very, very small, mostly the backward reaction happens. So with strong acids, everything just comes apart because it has a large Ka. So our H3O plus concentration comes from moles of H plus over the total volume. Okay, so if we take a look at our ionization equation with HCl and water, we get a one-headed arrow because it only comes apart, and we get H3O plus Cl minus. Right, so if my H3O plus concentration is moles of H plus over total volume, my moles of H plus come from my volume and molarity of HCl, which I had 1 milliliter at 0.1 molar. 0.001 liters times 0.1 moles of H plus per liter means that I have 1 times 10 to the 4 minus 4 moles of HCl, or H plus. So my total volume here, remember we're adding 1 milliliter to 10 milliliters of pure water, so my total volume is 11 milliliters. Right, so my concentration of H plus, or H3O plus, 1 times 10 to the minus 4 over the total volume in liters gives me a H plus concentration of 0.0091. Right? So the pH, because we added to pure water, our pH is 2.04. Right? So pH of pure water is 7. Right? So we see a difference, a change, a delta pH of almost 5. Right? By adding 1 milliliter of acid to 10 milliliters of water. Right, now let's take a look at what happens if we do 1 milliliter of acid to 10 milliliters of buffer. And like I said, we're going to use the buffer from the previous example. So we had nitrous acid, and it's a weak acid, so we make it an equilibrium. Will give us H3O plus our nitrite ion. Right, so what we're going to do here is we're going to add acid. Right, so if I add acid to the right side in the form of HCl, our ball rolls and shifts left. Okay, so this is where Le Chatelier comes into play. It actually is useful, right? And this is an example of the common ion effect, right? With my buffer equation, I've got some acid there in the form of H3O plus, right? Hydrogen ions, right, or protons. So if I add some HCl, I'm adding more of the same ion, right? More of that H plus, right? So common ion effect shifts the reaction up on the right side, which makes everything go left. Right, so when I have a buffer and I add acid to it, I need to use an ice table. Okay, I can't just go straight to Henderson-Hasselbalch because I need the equilibrium concentrations of my buffer components. Okay, and anytime you see that idea, you need the equilibrium concentrations, you have to use an ice table. Right, so let's write our equation again, because Dr. Lyon keeps shifting the page down. H3O plus aqueous and NO2 minus aqueous. Right, so in our previous example, we started with a buffer that was 0.3 molar of the nitrous acid and 0.6 molar of the nitrite ion. Right, or in the case of actually making the buffer in real life, I would start with some sodium nitrite. Right, and then with adding with our acid, we are now going to start with a concentration of H3O plus. Right, so we're adding acid. Let me put this in red. Right, so because that's going to affect the components of the ice table. Right, and so we figured out what the H3O plus concentration was in the previous example, which was 0.0091 molar. Right, that doesn't change. I still have 1 times 10 to the 4 moles of H plus from the HCl. My total volume is still 11 milliliters because I'm putting 1 mil in 10 mils of buffer. Right, so my H3O plus that I'm starting with here is the same as in the previous problem. Right, now our reaction shifts left. So in my change line, I'm going to say minus X, and plus X. Right, now all of that acid that I just put in there is going to get neutralized by my base. Right, so that's the way buffers work. If you add acid to a base, add acid to a buffer, the base neutralizes it. So my NO2 minus is going to neutralize that acid. So in my equilibrium line, my acid is going to be 0. Okay, so that means that X is 0.009. Okay? And I know that it's going to neutralize all of the acid because I will still have some base left over. Okay, it's a 1-to-1 ratio, acid to base. So I'm still going to have some of that original 0.6 molar base left over, right, after all of the acid is gone. So I can calculate my equilibrium line as 0.309 molar HNO2 and 0.591 molar base. Okay, so all of the acid gets neutralized. Right, that's why we end up with 0 for the H3O+. Right? Now, I can put into the Henderson-Hasselbalch equation. Right, because now I have the equilibrium values. And our pKa, so we're, from the previous problem, our Ka for HNO2, 7.2 times 10 to the minus 4, which makes our pKa 3.14. Right, so pH equals pKa. This is our Henderson-Hasselbalch equation. pKa plus the log of the base at equilibrium over the acid at equilibrium. And we're talking about the weak acid and the conjugate base. Right, so pH equals 3.14 plus the log of my base, which is 0.591, over my acid, which was 0.309, equals 3.42. Right, now the pH of the buffer itself, before we added acid, was 3.44. Right, so we see in this case a delta pH of 0.02. Right, so adding acid to a buffer causes a much smaller pH change than adding acid to just pure water. And this is the purpose of a buffer, is to resist pH change. Now, buffer ranges, right? So buffers are not sort of universally able to resist any amount of acid or base, but buffer range, put it in quotation marks, is about, this is not precise, but it's about plus or minus 1 pH from the pKa. Okay, so if my pKa is 3.14, then my buffer is only going to be good up to about 4.14 or down to about 2.14. Okay, and the reason for that is the ratio, right? So remember, our ratio for buffers is from 0.1 to 10, right? And that's the ratio of conjugate base over acid. Right, so it needs to be, the ratio of base to acid needs to be between 0.1 and 10 for the buffer to work. Right, so let's take a look at sort of some mathematical sort of proof of buffer range. So if I stay in that ratio, and if I say NO2 minus is 0.1 molar, and HNO2 is 0.01 molar, I get a ratio of 10. So pH equals 3.14 plus the log of 10 gives us a value of 4.14. If I reverse that, let's say if I've got NO2 minus is 0.01 and my HNO2 is 0.1, I've got a ratio of 0.1, then the pH equals pKa plus the log of 0.1. The answer to that is 2.14. Right, so all you need to know about the possible range of a buffer, right, how far it's likely to be able to function, plus or minus 1 unit from the pKa. So if my pKa is 6, my buffer will work up to 7 and down to 5. Right? Now buffer capacity, on the other hand, is a slightly different topic. So buffer capacity is a description of how much acid or base can be added before appreciable pH change. Right, so buffers are there to resist pH change. So adding more acid or base than the buffer is able to handle will cause a significant pH change. Okay, so in the previous example, we added acid that was within the buffer's ability to resist that change. But let's take a look at what happens if we add way more acid than the buffer is able to handle. And the good news about this topic is it is pretty easy to tell whether or not the buffer is going to break down. Okay, so let's say we have the same buffer system. And it is 0.6 molar sodium nitrite and 0.3 molar nitrous acid. And just as a reminder, to be able to, even if I didn't tell you this is a buffer, right? If I told you that these two components were in solution together, I hope that you'd be able to recognize that sodium does not play a part in anything, it's just a spectator, but I have NO2 minus and its conjugate acid, or the acid HNO2 and its conjugate base. Okay, a weak acid and its conjugate base create a buffer, right? So let's take a look at what happens when we add a lot of acid. So HNO2 plus H2O, H3O plus NO2 minus. And initially we have 0.3 molar of this and 0.6 molar of this. Now let's say we add 0.7 molar of acid, right? We take some hydrochloric acid and we dump 0.7 molar worth of hydrochloric acid in this buffer, right? So we're pushing up on the right-hand side of the equation, so the equation's going to shift left. So we'll have a minus x, and a plus x. right? Because we're adding to that H3O plus. Right, so in our change line, we'll have 0.3 plus X, 0.7 minus X, and 0.6 minus X. Right, and we can go through the quadratic, and I'm not going to belabor that process. And we find that X equals 0.581. Right, so my H3O plus .7 minus 0.581 means that I still have plenty of acid left over. Okay, so there wasn't enough base to neutralize all the acid. All right, and we would, if we complete our calculation here, our NO2 minus means that I've got almost no base left. All right, a significant amount of acid left, almost no base left, and by the time I'm done, I have even more of my weak acid. Okay, so the system cannot handle that much acid. Now, how do we tell? So in this particular example, we have 0.6 molar of the base and 0.3 molar of acid. Okay, so our buffer cannot handle more than 0.6 molar acid addition or 0.3 molar base addition. Okay, so the buffer's capacity to resist pH change is dictated by the concentrations of the components. Right, so when I add acid, my base neutralizes it. So I have to make sure that I don't add more acid than I have base. Right? If I add more acid than there is base, then there's still going to be acid left over. Conversely, if I add more than 0.3 molar base to my system, my acid has to take care of that, which is the HNO2. So if I add more than 0.3 molar base to this situation, I don't have enough acid left over to neutralize it all. Okay, so telling what the buffer capacity is directly related to the concentrations of the two components. Right? So buffers are best when the acid and base concentrations are the same. Okay, and at high concentrations. Right? So that way you can add a lot of acid or a lot of base and still not run out of your buffer components. Say this high concentration part is important. So if the concentrations of the components of my buffer are low, they're not going to be able to handle the addition of very much acid or base and still maintain pH. But if my concentration of the components are high, so for example in our worked out thing here, if my concentrations of buffer components were 1 molar each, all of that acid would get neutralized and we would still resist the pH change. Okay? That's going to do it for this particular video. We will come back with the next video talking about titrations and titration curves.